The average person, if you won $1 million, you'd be pretty happy. But if you won $2 million, you probably wouldn't be twice as happy, maybe 1.5 times as happy, or 1.33 times as happy. So there's a kind of law of diminishing returns. The fact that your happiness doesn't scale with the amount of money you've won is an example of non-linearity, and that's a crucial feature of chaos.
Knowing that this kind of situation is all around us, can we really predict large outcomes from small things?
What chaos theory is telling you is that there is a limit to how far you can predict into the future. I'll never be able to tell you exactly what the weather's going to be like over London 10 years from now to the day. Again, this is another aspect of the non-linearity of the system. The errors, if you like, grow very, very, very slowly. For a case of weather, it might take a month before those butterfly effects, grown in scale and amplitude, that they really have changed the weather patterns.
Dr. Tim Palmer, in your words, what is the butterfly effect?
The butterfly effect is a kind of generic term for a system whose evolution can be extremely sensitive to very small changes. For example, very small changes in the starting conditions. So when you make a forecast, weather is the classic example. When you make a weather forecast, you have observations of the weather around the world, and you try to create a kind of a global state of the weather from all those observations, and then you have a computer model which makes a prediction about what will happen a few days into the future. But of course, the trouble is that the observations are never precise, and they don't cover every single part of the globe. So there are always going to be small uncertainties in your starting conditions. And the butterfly effect says that there can be situations where those uncertainties can grow very quickly, and they lead to big errors in the forecast. Equally, you can get situations where the butterfly effect doesn't really kick in, at least for a very long time, which means that these uncertainties are not so important, and they don't affect the quality of the forecast. So the real question is, can you determine ahead of time whether the butterfly effect is going to be, operative or not? Because that basically determines how confident you can be in the forecasts you make. Now, I spend a lot of time, looking at weather, but the same ideas apply just as much to economic forecasting, other types of forecasting, health forecasting, all these things. They describe what are called nonlinear systems. So systems where the response of a system isn't in direct proportion to the input. This is the notion of nonlinearity. So weather's a good example, but there are many others. And I wrote a lot in my book about why this is important at a practical level. And as I say, because it gives you an indication of whether this is a situation you can be confident about the forecast, or whether this is a situation where you have to be careful, and where you can only make kind of very approximate or probabilistic would be the technical word, I suppose, forecasts, where you only say the likelihood of something happening is X%, rather than say, yes, this hurricane or this storm will definitely happen.
Yes, and it seems that in culture we're taught to see a lot of things in life like this. There's that movie, Sliding Doors with Gwyneth Paltrow, where it seems that life can hinge on these moments. Do you see life like that, or is it particular to other systems?
I do. I do very much. And, one of my kind of hobbies, I suppose you could call it, or sort of side interests, is moments in history where, the whole outcome depends on one of these butterfly effect moments. Actually, one is to do with the weather. So there's an interesting example, and I gave a talk about this locally last year, which when we were celebrating the 80th anniversary of D-Day, Second World War. And it was a really interesting story because they knew. General Eisenhower was in charge of all the Allied troops, and he had to make a decision about when to launch D-Day. And there were actually very few days that were going to be suitable because they needed a full moon so that the gliders could land, pre-dawn, and they could see where they were going, that sort of thing. They needed the tide to be right, and the tide and the moon sort of. There were just about 3 or 4 days which were possible, and 2 of those were the 5th and the 6th of June. Then the crucial issue was the weather. Now, the generals all wanted to go on the 5th of June because they were trying to deliberately fool the Germans into thinking they would be attacking France at Calais, whereas they were actually planning to attack Normandy. And the longer they left it, the more they were worried about the Germans discovering that they were actually going to attack Normandy. So they really wanted to go on the 5th of June. And the weather forecasters were called in. And, there was a US weather forecast team and a British weather forecast team and one or two others. And there was a lot of disagreement about what the weather was going to be like on the 5th of June. It turned out that on a very sort of desolate village on the northwest coast of Ireland, there was a lighthouse, and the lighthouse keeper's wife was tasked with taking weather observations every few hours. And this was actually her birthday when she was tasked with doing the weather observations. And I could easily imagine, they'd been to the pub the night before, and probably the last thing she wanted to do was get up at the dead of night and take a weather observation. And I could easily imagine she might have thought, oh, well, to hell with it. Who cares if I don't take a weather observation at 3:00 in the morning? I mean, who's going to care? But she did. And it turned out this weather observation showed a massively dropping barometer, strengthening winds, all the kind of characteristics of a big storm coming in. This was something like the 4th of June. The weather observations got broadcast to Dublin, who then sent them on to London, who then sent them to the D-Day forecasters. And they realized that there was a storm coming and it would hit the channel on the 5th of June. Now, you could ask the question, what if they had gone on the 5th of June? The weather would have been absolutely awful. D-Day would have failed. It would have taken at least another year for the Allies to regroup and, re-prepare things. By that time, arguably, the Russians might have continued their advance across not only eastern Germany, but the whole of Germany, and arguably maybe even into France. And we would be looking at a completely different world scenario, completely different. So just that one weather observation, which is a kind of the human butterfly effect, which is this woman deciding, oh, well, I better go and take that weather observation, even though I don't really want to get out of bed, a nice cozy bed, and I've had a lot to drink and the rest of it. She did. And, it kind of changed history. So that's a really nice example about how, butterflies also affect human history. And, there are plenty of examples like that. I could talk at length about this, but I won't bore you. But that's a really nice example, which brings the weather and the human side together.
Yeah. And you say I won't bore you, but there's something fun about these stories where something seemingly trivial plays into something so grand. You highlight others in your book too. What do you think that fascination is?
As I was saying to you, the notion of the butterfly effect is not it's not just very, very, specific systems that have this effect. It's kind of generic to a large class of, what a mathematician would call a nonlinear system. And pretty much every system, it's very special systems which are linear, extremely special. Almost all systems are nonlinear. And so we're just seeing at play. Another example is the First World War. The driver who was driving the Austro-Hungarian Archduke around, kind of lost his way. He took a wrong turning. And the guy who assassinated him, who was going to assassinate him, but he had given up, trying to locate the Archduke. And it was just by chance. He was kind of in a cafe and he was kind of consoling himself that he'd failed to assassinate the Archduke, when all of a sudden, out of nowhere, this car appears with the Archduke, and the guy stops because he doesn't know where he is. He's taken the wrong turning and he's lost. So, if he hadn't taken the wrong turning, the Archduke wouldn't have been assassinated. If the Archduke wouldn't have been assassinated, all the dominoes that then fell, which led to World War I, and then of course led to World War II, they wouldn't have happened. So all I'm saying, I guess, is that this is a very generic. The butterfly effect applies to pretty much every system, even the solar system. We tend to think of astronomical motion of planets around the sun as being the sort of archetype of predictability. But actually, we know that on long enough timescales, that's not the case, and that there is considerable unpredictability of the motions of the planets, and it's most manifest in terms of the asteroids. We really don't know. We can't predict well the motion of asteroids, which is why we're always slightly worried that an asteroid might end up hitting the Earth and potentially wiping a lot of us out. But, as the famous French mathematical physicist Henri Poincaré discovered at the beginning of the 20th century, which in a sense was the beginning of the start of chaos theory, the planets are also chaotic. They're not as predictable as they might seem at first sight. And we still don't know, for example, whether in the distant future Mercury, might end up colliding with Venus or something like that. It's not impossible for that to happen, and that would then have ramifications. So it's very hard. It's actually very hard to come up with real life examples which don't exhibit the butterfly effect. I would say that's more the exception than the rule.
Mm-hmm. I wonder, is it something to do with the element of time in these stories? Is time that sort of non-linear ingredient that would do the trick because time can't go negative? How does that work?
Well, you have to have systems that are they have some kind of notion of instability. I mean, you can get, for example, if you imagined a football, or when I say football, I guess you guys would call it soccer ball. I mean, a circular ball on the top of a mountain, and you give it a little, a small kick, and then it kind of rolls down the mountain, and the velocity gets faster and faster. I mean, that's an instability, but it's actually not. That itself is not a non-linearity. The non-linearity would come, if the mountain, instead of being one mountain, it was, a whole collection of mountains, and the ball, was rolling down and then rolling up again, without much friction, and then trying to predict which mountain the ball would eventually, which valley or whatever. So you need that would be chaotic. So you need two things. You need this notion of a system that's potentially unstable to small perturbations, it would be called. And this non-linearity, I mean, it's a little bit hard to say what non-linearity means to a complete, someone who's got no mathematics at all. I think most people who know a little bit of mathematics would know what non-linearity means. But one way I kind of try to think about it, and I think I put it in my book, is that, if you won, let's say $1 million on the, the lottery or some kind of thing, you'd be really happy. You'd be really, really happy. I mean, assuming you're not a billionaire. So we're ruling out like Elon Musk here. But for the average person, if you won $1 million, you'd be pretty happy. But if you won $2 million, you probably wouldn't be twice as happy. I mean, you would be, maybe 1.5 times as happy, or 1/3 times as happy. So there's a kind of law of diminishing returns. And that sort of, the fact that your happiness doesn't scale with the amount of money you've won is an example of non-linearity. And that's a crucial feature of chaos. But, time going negative, I don't know whether that is so much of an issue. I mean, the fact that these are systems that evolve in time, I mean, they're not just static systems that do nothing. I mean, that's important. So the system has to be a system that can evolve in time. But if it's unstable and non-linear, those will be the two key mathematical ingredients for chaos.
Mm-hmm. So knowing that this kind of situation is all around us, can we really predict large outcomes from small things?
Well, yeah. So again, what chaos theory is telling you is that there is a limit to how far you can predict into the future. And, in the case of weather, you know, I mean, you could certainly say, I can't tell you, I'll never be able to tell you exactly what the weather's going to be like, over London 10 years from now to the day. I mean, whether it's going to be sunny or rainy or, whatever. That's kind of impossible. But in a way, that's not the aspect that interests me or interested me in studying this phenomenon. Again, this is another aspect of the nonlinearity of the system, that sometimes for some initial conditions, a small change to those initial conditions actually doesn't have much effect for a very long time. I mean, the butterflies, the errors, if you like, grow very, very, very slowly. And it might take, for a case of weather, it might take a month before those butterfly effects have grown to such an extent, that grown in scale and amplitude, that they really have changed the weather patterns. But there are other situations where these uncertainties grow so quickly that within a couple of days, they can affect the weather, for example. The same, by the way, is true of the economy. I mean, sometimes we can make predictions about, the rate of inflation or, sort of, GDP or something like that pretty well for, a year or two ahead, and they're quite accurate. But again, you get these very kind of periods where, the system gets very unstable, and it's almost impossible to make predictions more than, a few weeks or a couple of months, maybe at most, ahead. So the question is, can you predict where those, essentially these are regions where the instability is especially large. Can you predict those ahead of time? And I worked a lot on what are called ensemble prediction systems, where you basically run your models, many times, 50, 100 times, changing parameters and initial conditions very, very slightly. To see ahead of time, is this a situation where all of the predictions are kind of diverging from each other very, very quickly? Or with this is a situation where the butterflies aren't actually growing particularly quickly, and, all the ensemble members agree with each other very closely. And then you can make a very definite prediction. But in the case where they're growing rapidly, you might still want to see whether there are any of the solutions, for example, which have extremely severe weather. For example, there might be some incredible storm which blows up over a couple of days. And when you try to make a prediction, the best you could say maybe is there is a 10 or 20% chance of this storm happening. Now, that could be large enough for some people, nevertheless, to say, well, if I was planning, to sail my yacht across the English Channel and there was a 20% chance of a hurricane, maybe it's not a good idea. It's like, people often say, if you checked into an airplane, your airplane flight, and the guy says, oh, well, we've discovered some cracks in the wings, but don't worry, there's only a 10% chance the wing will drop off. You wouldn't take that flight. So 10%, can be enough of a probability sometimes for people to take action. So now I just, I contrast that with when I started in the field. All the predictions were very deterministic. People would just try, the weather forecasters would just try to predict the most likely outcome. And the feeling was, people aren't interested in uncertainty, or it's too complicated or whatever. But that hasn't, that's not the case at all nowadays. For example, we all are familiar now with probabilities of rainfall from our weather apps.
Yes, that's how we see it now.
That's how you see it.
20% chance of rain today.
Exactly, and that 20% chance means that 20% of the ensemble members actually, this is an important point because people sometimes ask me that question. What does 20% mean? Does it mean it's going to rain in 20% of the city or on 20% of the time, or what does it mean? It means that in 20% of those ensemble members, like we might run 100 ensemble members, let's say, so in 20 out of 100, it's raining over your favorite town at your particular time that you're interested in. That's what it means. 20% of the ensemble forecasts predict rainfall, but 80% don't. Now, the question is, if, maybe we can just go on to this for a second, because this has important ramifications, I think, for climate change as well. The question is, what do you do with that information? I mean, let's say you're about to go hiking, up in the hills, and you look at your weather app and it says there's a 20% chance of, some pretty significant rainfall. What do you do? I mean, the weather forecaster can't answer that question for you because it's not a scientific question. So, you have a choice. You either don't go for the hike, you do go for the hike, but you take some waterproof gear, or you say, well, 20%, that's not worth worrying about. I won't take any waterproof gear because, after all, waterproof gear is pretty heavy, and I've got to put them in a backpack, and it's just a pain. So you got those three options, and in a sense, well, more than in a sense, it is up to you to decide how you're going to act based on that information. It's certainly not the weather forecaster's job to tell you whether you should go for that hike or not. If you don't pack the waterproofs and you get wet, then you'll be soaked and it's be extremely uncomfortable. I mean, if it's right up in the hills, it might even be, there's a danger you might get exposure and, extremely cold. On the other hand, if you do pack the waterproofs, they're heavy, and it maybe doesn't add to the pleasure of going for the walk, But that's your choice as an individual, and the weather forecaster can't tell you that. You have to make that decision yourself based on that information.
And for those who don't know your story, you have your own sort of career butterfly effect moment that then takes you to this point where you've had a big influence in how we all get the weather now. What is your sort of story professionally into this field?
It's yeah, I mean, it's a little bit butterfly effect-ish, perhaps. And I mean, I started off, as a kid, I've always been interested in science and physics. I mean, I can remember as a even like 10 or 11 years old, being fascinated by like many of my, like many people, many young children, being fascinated by the night sky and the stars and all that sort of stuff, astronomy. And I got to know all the constellations and stuff at quite an early age. And I decided I wanted to do, and I read somewhere some books on Einstein's theory of relativity and the idea about, time being relative and all that sort of thing, which I just thought was such a kind of a cool idea that I really wanted to study that for a PhD. So that's what I did. I did an undergraduate degree in mathematics and physics, and then went on to Oxford to do a PhD in general relativity, so Einstein's theory of gravity, basically, which was tough. It was tough, I have to say that. I mean, trying to make a significant impact in a field that is pretty, has a lot of extremely talented people working on it is difficult. But I got there in the end, and I was kind of pretty happy with what I achieved. And I got offered a position actually to work in Cambridge with Stephen Hawking, which was I think that was quite an achievement actually. And
yes, you mentioned talented people in the field. I mean, let's not downplay that. Everyone knows who Stephen Hawking is now.
Right. Yes. Right.
And you knew him in the time when he was still speaking and things.
Well, I the first conference I ever went to, which was literally when I was starting as a graduate student, he still had his voice. I mean, he didn't speak all that clearly. So, and he had obviously difficulty speaking, but he could still speak. And I actually attended the conference where he announced what now has become his unquestionably his most famous result, which is that black holes evaporate. They don't just get bigger and bigger. They actually can actually radiate energy. And I can remember, on the bus on the way back into Oxford, the conference was actually just outside Oxford, but we had a little minibus taking us all back afterwards, and there was enormous debate in the minibus about whether Hawking's result, was believable or not. I mean, there was an eminent, I won't mention his name because it would embarrass it. Well, he's since passed away, but eminent professor who said it was all complete tosh. I mean, everyone knows black holes are black. How can they radiate energy? How could, doesn't make sense. Whereas other people were saying, well, this is a landmark moment because Hawking is this is the first ever calculation where quantum mechanics and gravity and thermodynamics have come together. There's a lot of discussion about it, and it was kind of exhilarating. I could add nothing to the discussion because I was too junior, but I could sense I was at a kind of a moment in time where something really important was happening. And that's right. So I did think hard then about accepting the position at Cambridge. But I kind of, the more I thought about it, the more I wasn't 100% sure I wanted to spend my entire life doing what is basically very abstruse and kind of societally irrelevant work. And it kind of bugged me a bit. This area, the area is kind of what's called quantum gravity, where you're trying to combine relativity theory, general relativity theory, and quantum mechanics into a single theory. I should say we've hardly progressed probably from where we were in, that time, 1974, when Hawking announced his result in quantum gravity. And it did really bug me that I could spend the whole of my life probably writing loads of papers and things, but making no real impact either on, physics. I mean, if I discovered the right theory and won a Nobel Prize, I think I would have been pretty happy with that. But, I wasn't comfortable that we understood the problem well enough, or I certainly didn't understand it well enough to make progress. So I kind of and I also, it bugged me that, I could be spending the whole of my life doing something that turned out to be pretty useless, actually. And I kind of, the more I thought about it, the more I wanted to perhaps use my skills to do something more useful. I mean, a lot of people in those days a lot of people went into defense. I didn't really want to do that. Some people were going in, this is the era where people started going into the city of London to finance houses. I didn't want to do that either. I mean, nice to get rich, I suppose, but it didn't. And then I by chance, this is where the butterfly effect perhaps comes in. By chance, I met somebody who was quite a senior climatologist who, and as I say, completely by chance, I met this person, and they persuaded me to apply to the British Met Office. And I have to say, I got recruited because in those days they weren't overly bothered about whether you actually knew any meteorology or climatology. All they really wanted were people that were good at physics and good at mathematics. And I contrast that with today, where they probably feed all the applications into an AI kind of piece of software to pre-select the people that they interview. And I suspect the AI looks for experience in meteorology, experience in, in computing, all the things I knew zilch about. So I would not, in today's environment, I don't think I'd even get shortlisted based on my experience. And I do think it's an area where I think we're going wrong, and I'm digressing a little bit here, but the last 10 years or so, when I've been back at Oxford and advertising, postdoctoral positions and things, I've had lots of applicants from areas of, cosmology, high energy physics, number theory, very abstract mathematics and so on, who, they've done pretty much like me. They've done a PhD. They maybe have even done a couple of years of postdoc experience. And they've kind of achieved their childhood ambition of doing some research in this area, but they now feel they want to do something more practical and useful and, help society a bit. And today's the way research is organized and funded today, it's much, much more difficult to take those people on. I mean, I tried to make an effort to do so, but the system is not well geared. And it's because, as I say, we're just getting so siloized, and the boxes that you have to tick to get jobs, require you to have experience in precisely the area that you're planning to work in. And it's not good for, I don't think it's actually good for science, this kind of high degree of siloization. Yeah. Anyway, so all I'm saying is I was lucky back in the 70s to, I think that in a situation that doesn't exist today, that I was able to transfer fields relatively easily.
Yeah. And could I just add one thing? You said that this is sort of a digression, talking about, people from varying fields and things. And yet I think it's very much on the theme, because you are having this butterfly effect moment, and that you are the kind of professional who is noise in the system rather than one of many who are brought through a traditional track. So I see this as another look at the same idea.
I think you're right. That's a very perceptive point. I think you're absolutely correct. And when you look at when you look at people that have made breakthroughs in fields of science, and you ask them, where did that brilliant insight come from? You'll find that as often as not, in fact, probably more often than not, it's come from taking an idea in a different field and applying it into your field. It's not like, that idea's just literally come out of the vacuum or out of the ether from nowhere. It's often that somebody said, "Oh yeah, I can see how this idea in field X can be transported to field Y and have an impact." So having, as you say, noise in the system, which means kind of people who come from, different areas, even potentially randomly different areas, can have a big impact, and I think that's important. One of my mentors at Oxford was Roger Penrose. Played a big role in my thesis work, and indeed subsequently thinking about quantum foundations and things.
Yes, he started Penrose for those who don't know.
Sorry, say again?
Sir Roger Penrose, for those who aren't familiar.
Yes. Well, Sir Roger Penrose, but more importantly, perhaps Roger Penrose, Nobel laureate, from a few years ago now, not so many. But he got his Nobel Prize for work he did in the 1960s in showing that the singularities at the center of black holes and indeed at the Big Bang were not artifacts of spherical symmetry. So just to unpack that a little bit, people had been able to solve Einstein's field equations which are very nonlinear, incidentally, but providing they impose very, very strict symmetrical conditions. So the universe is precisely spherically symmetric, or a collapsing star is precisely spherically symmetric. And if the collapsing star is big enough, Einstein's equations show that it collapses to a black hole where all the mass is concentrated at the center of the black hole. But a lot of people, and that was discovered back in the 20s and 30s. But a lot of people, and that included Einstein, incidentally, thought that this was completely unrealistic, and that if you could solve his equations without this condition of spherical symmetry, then you'd find that actually, the mass of the star would just get, just spread out across space. It wouldn't concentrate in a singularity. And there was a paper by some Russian physicists who claimed to have proven that black holes would not exist under normal types of situations where you don't have precise spherical symmetry. Penrose started to apply ideas from pure mathematics, what's called sort of differential topology, which is something that he had learned as a mathematics PhD. See, his PhD wasn't in physics, it was in mathematics. And he decided to pivot, if you like, change fields into physics after his PhD. And he realized, I mean, it's extraordinary insight, but he realized that these kind of more, what are called qualitative mathematics. So topology is often cited as a kind of qualitative mathematics because a sphere and a sort of, I don't know, well, like a British soccer ball, which is precisely spherical, and an American football, which is kind of, squidged in at two ends and so on. These are topologically identical. So, topology is a more qualitative kind of type of mathematics. Anyway, he showed that these ideas in topology could be used to show that spherical symmetry didn't matter. This was the point. Now, of course, everyone said, but the Russians have shown the opposite. And the Russians went back to their paper and they realized they'd made a mistake. So Penrose won out, and ever since then, people have taken black holes seriously. So pre Penrose, they didn't take them seriously. Post Penrose, I'm talking about 1960, mid 1960s, 65, I think it was. So post 1965, people took black holes seriously, and post 65, black holes have now become the center of pretty much every aspect of astrophysics and cosmology. I mean, they are, they're at the center of all galaxies, supermassive black holes. And we've had now, these telescopes, the Event Horizon Telescope and other telescopes, which have, and indeed LIGO and things, which have pretty much shown that black holes exist. We know that black holes exist. So that was the basis of Penrose's Nobel Prize, the fact that he showed that they were robust and that they exist experimentally. Now, again, butterfly flap moment. If Penrose hadn't changed fields, my guess is to this day, the Russian paper would still be cited as evidence that black holes don't exist. Mm-hmm. And so we were gone through the 70s and 80s and so on. People would not have built these telescopes or LIGO or any of these things because they said, well, black holes are just artifacts. They don't really exist. And I think, the whole of cosmology and astrophysics could be in a completely different place.
Right.
So Penrose deciding to change fields, just kind of qualitatively changed the whole of astrophysics and cosmology. It's hard to underestimate how important that paper was.
Yeah. And Tim, in your journey, so you're having these moments, you're encountering these people who are icons in your field, Stephen Hawking, Sir Roger Penrose. How do you go from that moment where you get involved with meteorology to now science that we all engage with, on our weather apps and things?
Well, it's because I get a buzz. You see, I do get a buzz out of. Let me give you a very specific example of where I got a buzz from. You see, the problem is, if you're a Roger Penrose, you write a paper that absolutely changes the field, or even indeed Stephen Hawking did with his evaporating black holes. I mean, of course, there's no denying who wouldn't like to do that. Of course, everyone would like to do that. But you have to remember, for every paper like that, there are 10,000 or 1 million papers probably, which are pretty humdrum by comparison. And maybe get 3 citations or something, or even some, a lot of papers get 0 citations. I mean, this is the downside. So I decided I would get a buzz out of doing something that had practical importance. And where I got a big buzz was when I read about a program called Anticipatory Action, which is now has completely revolutionized the disaster relief programs and the humanitarian aid programs. So again, if you think about in the sort of old days, right? Old only means like 10, 20 years ago. What would happen is a hurricane would hit, or a tropical cyclone, or some kind of extremely severe weather event would hit a place. I mean, let's say we're talking about parts of the world, what we call the global south now, parts of the world where people are extremely vulnerable to extreme weather, and where in the 1970s, before weather prediction really became a serious science, I mean, when a tropical cyclone would hit a place like Bangladesh, it could kill 100,000 people, because they were completely unprepared for not just the winds, but the storm surges, the flooding that would occur when the storm inundated the low-lying regions and the islands and so on. But even when these weather forecasts came, still the aid agencies were reluctant to take precautionary or sort of, action ahead of time, precautionary action, because they knew that for every successful, accurate weather forecast, there might be 10 which were not accurate. And they all had limited resources. All these agencies are funded with limited funds. So they can't afford to send medicine and shelter and food and water to a particular region that's predicted to be hit by a hurricane, when 9 times out of 10, that won't happen. It's just, a waste of their resources, and they very quickly go bust. So what happened was that they would just wait. I mean, they would wait. And then when the storm hit, wherever it hit, if assuming it did hit, then that's where they would go after the event to distribute water and medicine and so on. But the problem then is that, it can take several days to reach a stricken location if the roads are down and they're blocked by debris and all the rest of it. I mean, and people die in between, and it's very difficult. So what happens now is that this is a really good example of how to use a probabilistic forecast. So they say to themselves, okay, we know how much money we've got. We know how much, what our supplies of emergency shelters and medicine is, and so on. We'll work out ahead of time how high a probability the forecast has to be of this extreme event for us to take precautionary action. Okay, so if it was like 90% or 100%, you'd say, well, obviously that's high enough a probability to take precautionary action. If it was 0% or 10%, it's probably not high enough to take precautionary action. So then the question is, well, what is the threshold? So you do a kind of a detailed cost benefit analysis, and you come up with a number, and it could be, I don't know, say it's 75%. But you've made that calculation. You've done that prior to making a decision. You've done that, if you like, offline. So okay, now I know if the event is predicted with greater than 75% probability, I will send in, the head of this humanitarian aid organization, will send in emergency supplies to the region predicted to be at risk. And if it's less than 75%, I won't. And that is precisely how to use probabilistic information for very concrete and very specific decisions. Some people sometimes say to me, well, how can you, it's just so wishy-washy probabilities. How do you ever decide? Well, this is a very good example of exactly how to decide. You work out ahead of time what your probability threshold is, and you take action. Now, I gave a more amusing example of this in my book. It's the same philosophy, but it was somebody who called me up about whether to hire I guess what you guys would call a tent, and we call it a marquee to, in your garden. He was having a significant wedding anniversary or something, and I had the option to hire this tent and wanted to know when it was going to rain. This was something like 10 days before the event. He had to decide, if he left it any later, it wasn't going to be available. And I explained, I'll give you a probability. And he kind of groaned. I could hear at the other end of the telephone line this kind of groan. Oh, God, why do you just tell me, is it going to rain or is it not going to rain? And I said, I'm sorry, but this is not the way, this is not the way science is. But I said, look, we can talk through this because who's coming to your party? And he said, well, what's that got to do with it? And I said, well, it's the Queen. It's the Queen coming. What's that got to do with it? Well, look, if the Queen was coming and there was even a 5% chance of rain, you would surely hire that tent because if the Queen got wet, it would be a disaster, wouldn't it? He said, well, I see what you mean. Yeah. No, the Queen's not coming. Well, how about the town mayor? What's that got to do with it? Well, look, if the town mayor got wet, it wouldn't be as bad as the Queen getting wet, but it still would be a little bit embarrassing for you. The big town mayor appears with his medals and, gets wet. So we could say 20% chance. If there was a 20% chance of rain, you might hire the tent if the town mayor is coming. He goes, no, the town mayor's not coming. So who's the most important person coming? He sort of thinks about it. Probably the mother-in-law. So I said, well, okay, you got the idea. What's the probability? What probability of rain would there have to be for you not to want, the mother-in-law to get wet? And I think 40%. So I said, great, we've got a decision. We've made a decision process now. I will go down and look at the maps. I will tell you the probability. If it's more than 40%, you'll hire the marquee. If it's less than 40%, you won't. Right? And he agreed. So I think it was 20%. He didn't hire the tent. It didn't rain. He was very happy. So, but the more important point was that this is exactly the same type of decision that a humanitarian agency would make, but under, perhaps more extreme situations. But it gives you the general idea.
Yeah. What was it like normalizing that process? Because as you said, your friend, he has resistance. There's a certain comfort in, someone says it's going to rain. For those humanitarian organizations, did it take time to get buy-in? Did you see maybe a moment when it worked and then it clicked and then you could tell others?
Well, that's an interesting question because I did get quite a lot of flack at the beginning. Actually, less from, if you like, the public, but more from colleagues. And there were two types of colleague. One was my kind of research colleagues. And I think that they were just, you see, the point is, if you run your model, 50 times or 100 times, it's taking up computing time. And everyone had their own idea about how to use computing time. So there was always a battle, if you like, because, this was in the era of what's called Moore's Law, where computers would pretty much double in speed every 18 months or so. So, we would start discussions a good 18 months before the procurement of the next big supercomputer and discuss how we're going to use the computer time. And of course, I was arguing for these ensembles. And a lot of my colleagues said, oh, no, we need to improve, some aspect of the model that would take up time. Everyone had their own ideas about how to use the computer time. So that was one kind of area of resistance. The other was from actually the weather forecasters who were, perhaps dealing with the public or dealing with, the media and things like that. And they were kind of resistant because they felt that probabilities were too complicated for the public to understand. I think, to be honest, what was a little more behind it was that in those days, the forecasters would often, they would take a computer output, the raw computer output, and they would kind of tweak it a little bit themselves. They would say, okay, I think the model tends to, move storms too far to the north, so I will kind of move this storm a little bit to the south. They would apply some manual intervention to the computer model as a post-processing the computer output. The problem with probability is that it's very hard. You don't have any intuition about how to kind of modify probability. So I think that was the real reason why they weren't very keen on these things, because they felt they were not able to apply any of their kind of human expertise, if you like, to modify the forecasts. But over the years, the models have got so much better that actually there's very little a human now can do to improve the forecasts. They're just kind of, they come straight from the computer model. Yeah, and so as I say, more the resistance actually came more from colleagues than, say, from the public. I mean, whenever I talk to, I used to give talks to the public and say this could be the way in which weather forecasting will evolve. What do you think? And actually, people got it, and they were pretty comfortable, actually, I think. So,
what was it like to have a success, to see one of these humanitarian efforts, make that cost decision and work it out?
Yeah, fantastic. And as I say, it kind of it just made me think that my decision to change fields back in the late 70s was the right thing to do. The idea that something you've done potentially affects millions of people around the world is quite it's kind of a humbling thing in a way, because you're just fiddling around with bits of computer code and stuff. But to think at the end of the day, it's not just in England that I've had an impact. It's in Bangladesh, it's in China, it's in Australia, it's in Africa, it's everywhere. And that's that, as I say, that's given me the a feeling that I think I made the right decision.
Mm-hmm. Do you remember a specific one or a first?
Well, yes, yes, I do, very much so, because I had a colleague of mine who I'd kind of worked with for a number of years, whose name is Peter Webster, who's he's now just retired from the Georgia Institute of Technology, Georgia Tech in Atlanta. He spent a sabbatical year working with me in England, and got very enthused about the work we were doing in probabilistic forecasting. And he decided to spend a year completely stopping his normal kind of research work, and got a grant to travel to Bangladesh. And not only, this is not just to go to the Met Service. He went out to individual villages in rural Bangladesh on the banks of the Brahmaputra River and the Ganges River. And he set up a system whereby I think it was the village imam, who was the kind of chief guy that people looked to for advice, about situations. And again, he would discuss with them about, okay, we're going to try to forecast when the Brahmaputra or the Ganges is likely to flood. And, we're going to try to give you, let's say, 4 or 5 days notice of this flooding, so that you can, first of all, get your livestock onto higher ground. That could take, several days. And ensure that people living in these islands in the river were evacuated. And of course, again, the discussion came up about probabilities and how high a probability should trigger movement of people or movement of animals and so on. But the village people got it. They really did get it, and they agreed on the strategy. And Peter worked for a whole year with these villagers. And there were, in fact, I think he worked for 2 separate flooding seasons on this. And there were several occasions where this exactly happened, that the probability threshold was exceeded, and that the village elders decided this was the time to move the livestock and as I say, in some cases, the people themselves from the islands. And they actually could quantify how much they had saved, because they know how much a cow or something is worth and so on. So and it came out to be a remarkable, I mean, as a fraction of the annual income of these people, it was an enormously large number. So that was, I mean, that actually, in a way, Peter Webster's work, sowed the seeds for this anticipatory action that subsequently now all the leading charities and disaster relief agencies use. I mean, he demonstrated that this really worked, and he deserves a lot of credit for that. But that was the first time when I realized, yeah, this is not only working, but it's something that people at the ground level understand and they get.
Yeah, so exciting to have your colleague on the ground too, to have somebody like that. So you feel that connection. Could we take just a quick detour into something you said earlier? You said Moore's law as though it's a past tense thing. Are we past Moore's law? What is Moore's law, and what's happening with it?
Yeah, that's a really good question. So Moore's law was, Moore was one of the pioneers of computer architecture and computer chips, and he predicted back in the I don't know when 1970s, I think, that the technology of transistor miniaturization was improving so rapidly that, for a given chip, of a given size, in 2 years or 18 months or something, you'd basically be able to double the number of transistors on that chip. And not only that, because the transistors were smaller and so on, they ran with less power. So for the same, the same input energy, you'd be able to double, with transistor miniaturization, you'd be able to double the number of calculations you could do per second and per watt of electrical power. So we went through this era of, I wouldn't say Moore's law exactly is finished, but it's kind of asymptoting out, because the problem is that you eventually get down to this where transistors are not that much bigger than an atom. There are several atoms in size. So then, if you think of computing as something, this raises another topic, but if you think of computing as something where you add 1 and 1 and it gives you 2, or you add 2 and 2 and it gives you 4, and that's, that is absolutely what it tells you, then, you can't afford to have transistors that are not reliable, so that you don't want to somehow get 2 + 2 = 5 because the transistor hasn't worked properly. So basically what that means is there is a limit to how much miniaturization you can do of transistors, and you get down to the stage where what's called quantum tunneling affects the reliability of the transistor. So Moore's law, where basically computer power doubled every 18 months, was a period where there was an enormous growth of applications which use high performance computing, like weather prediction. But we're running into the stage. So we've kind of got to the stage now where computers, the big computers, just get bigger and bigger. So you rather than being able to make the chips smaller and smaller, you just add on more computer boxes. So you have more and more chips. The problem there becomes then you've got to distribute your calculations across all these chips, and you have to do what's called massively parallel computations, where you distribute all the calculations across gazillions of chips. The problem is then you have to collect all that information back again, and it turns out that the cost of transporting the data, the bits of information from one part of the computer to the other, is extremely energy intensive. And that's why when, from years where the power requirements of computers didn't change that much, now they're getting more and more power intensive. And, a modern top of the range supercomputer would be consuming, I don't know what it is now, 40 megawatts or something of power, which is, when you think about the brain, operates with 20 watts, so six orders of magnitude less, and arguably does similar amounts of data kind of analysis. If you think of all the billions of bits of information that come through your eyes and in your ears every fraction of a second, and the brain's got to sort all that out and make sense of it. I mean, it does that with the same level of data processing that a supercomputer does, but it does it with 6 orders of magnitude less energy. I think that's a really interesting fact of the matter.
Yes, and this ties back nicely to sort of this arc of your career so far, because we can talk about what you've learned regarding efficiency, letting noise into the system. What are the benefits of that?
Well, yes. I mean, just to come back to the butterfly effect, if you like, and the ensemble forecasting business. I mean, I spoke about the fact that, the initial conditions of a forecast are never certain. The observations are never precise, and they don't cover every part of the world. So the initial conditions are uncertain. But actually, that's not the only source of uncertainty. And we know kind of what the equations of fluid mechanics are. The atmosphere and the oceans are really governed by the equations of fluid mechanics. So things called the Navier-Stokes equations. They're 19th century. Navier was a French scientist, and Stokes was an Irish scientist, physicist. Navier-Stokes. These are well-known equations, but you can't solve them kind of directly. They're too complex. So you solve them on a computer, but the computer, because the computer's finitely sized, you're going to make some small errors in actually solving those equations. And that is a secondary source of uncertainty. This is, again, another area where, my colleagues didn't see eye to eye for some time. I used to argue that to represent that uncertainty in the computational representation of the Navier-Stokes equations, we should add noise to the equations. We'd actually make them what are called stochastic, so they would have noise built in explicitly. And this kind of seemed, people didn't like that idea because they, surely noise is going to make the forecast worse. If you make them noisy to make it worse. I said, no, this is a nonlinear system. Nonlinear systems, noise can be your friend rather than your enemy. And people said, well, give me some examples of where that's clearly the case. And that kind of that's what got me interested in the brain, because the brain is very certainly a noisy organ. Books have been written called The Noisy Brain. And arguably, the noise has come from the fact that we've evolved this incredible, our neurons are incredibly small, so small that we can that nature has managed to squeeze 80 billion of them into our skulls and operate them with just 20 watts of power, which is tiny. Per neuron, it's absolutely tiny. And we know from experiments that with that tiny amount of power, the operation of a neuron is not going to be completely deterministic. It's going to be susceptible to noise. So the question is, why would we ever evolve with such a system which is noisy if noise was going to be detrimental? I mean, it runs completely contrary to evolutionary theory. Evolution only works if it's advantageous, if the mutations, that's the word I'm looking for, is going to be beneficial. So mutation to randomness has got to have some benefits. And, I began thinking about this, and it strikes me that the whole way that we work, when we make decisions, when we operate as creative people, we're actually exploiting this noise that's in the brain. Because otherwise, I mean, a good example actually of, and I think it's a good example for how the brain works, is an algorithm called simulated annealing, which is sort of about trying to find the minimum of, or the maximum, whichever you like, of a function which has many local minima. So you start off at some point on this function, and you say, let's try to find the minimum, and you just go downhill. Now, a normal kind of what's called a deterministic algorithm like that would stop when you get to a minimum, because then the only direction you can go is uphill. But what you don't know with that algorithm is whether you've actually reached just a local minimum and not the global minimum of that function.
And for those listening, just to follow along, you kind of picture like a curve, like hills, and you might be in the valley between two hills.
Exactly.
So if you're looking for the lowest point, you might be looking for a much lower valley.
Exactly.
That you just haven't touched yet.
That's right. And I don't think I'll go into this in detail, but simulated annealing is a stochastic. It's an algorithm which adds noise, and it kind of allows you to explore the possibility that that minimum that you have landed in is not the global minimum, but just a local minimum. And I think that's the way we think. We might try to find a solution to a problem, and we kind of come across a possible solution, but we're not really sure whether that's the best solution. And in trying to this is the way I think, in a way, well, it's not just me, it's almost universal feeling of when people have creative ideas and they say, well, where did that idea come from? And they say, oh, it's usually when I was just, I was having a shower, or I was just walking across. I mean, Penrose has the example. I was walking across the road looking at the traffic. Or, something completely nothing to do with the problem at hand. It's kind of noise. Noise has created something. And, most of the time we probably have these kind of noisy ideas and they're no good, and we just very quickly forget about them. But occasionally we have one that, triggers the eureka moment and takes us out of that kind of local minimum where we'd sort of found a possible solution that wasn't quite good enough to one that really works. So anyway, I've certainly become a big believer that for nonlinear systems, noise. You shouldn't think of noise as your enemy, but as your friend. Treat it with great respect. So anyway, so again, that was a battle that took a while. But I think these days, certainly all weather forecast models use noise. The climate models are kind of moving in that direction, but they haven't. I would say haven't fully embraced it yet. But I'm hopeful in the not too distant future.
Yeah. What do you hope with climate modeling? Studies of climate change. You've written a paper recently about this topic.
I wish people would try to separate the science from the politics. So there are two sides to climate change. There is the sort of what does a molecule of carbon dioxide do to the weather, which is kind of it's not a political question. It's just a science question. It's something physics, can answer, physics and biology maybe. But then there's the second question of, is it worth us as a species trying to do anything about the problem? And that's obviously a political problem, because it involves value judgments. And again, I see it as very similar to the problem of, like the one, should you hire a tent for your wedding anniversary when the probability of rain is 20%? I mean, it's not a question that a weather forecaster can answer, because it involves value judgments. Like, do you care if the Queen gets wet or something like that? I don't know. Now, when you talk about climate change, in a way, it's not like a weather forecast in the sense that it's not really about, it's not what's called an initial value problem. This may be a little bit difficult to explain. We were talking earlier about what underpins chaos. And as you correctly said, it does involve things to do with time evolution and so on. When we talk about climate change, we're not actually answering that problem. We're not saying, like, we're not trying to say what's the weather going to be like in 50 years' time on this precise day, in London. That's not what a climate prediction is trying to do. What a climate prediction is trying to do is to say, if we carry on emitting carbon dioxide in the atmosphere, how is this changing the weather patterns? So it's not like, whether it will be raining in London in 50 years' time, but it's more saying, is the number of days where it's raining going to be more on average than it is today? Or is the number of days where the temperature exceeds 100 degrees Fahrenheit let's say in US units, is that more than it is today? So it's questions about the statistics of weather, changing statistics of weather. So because of that, it's not really, you see, some people say, oh, well, you can't possibly, if you can't forecast the weather more than a week ahead, how can you possibly say anything about the climate in 100 years, say, from now? And, that is to misunderstand the nature of the problem. As I say, the nature of the problem is to try to estimate how the statistics of weather are changing, in your region as a result of our emissions of carbon dioxide mainly, but there are other greenhouse gases, but let's say carbon dioxide for the sake of argument. Now, that's not to say there aren't uncertainties, and there are uncertainties in making climate predictions, and a very important one actually is, and probably the single biggest uncertainty, is the role of clouds. I mean, the thing that makes kind of the weather and the climate quite complex is the role of water. Water exists in multiple phases. We have, the gaseous phase of water is just water vapor. The liquid phase is water droplets. And then we have ice crystals as well in clouds. And these all have a very definite role in regulating the temperature of the planet. And one of the really big questions about climate change is how clouds are going to change as we increase the amount of carbon dioxide in the atmosphere. And the worst case scenario is that very high level clouds increase and very low level clouds dissipate, because low level clouds tend to scatter sunlight back to space and they cool the planet effectively, whereas high level clouds, which are kind of very wispy cirrus clouds, tend to trap heat more than they reflect light. So high-level clouds warm the atmosphere, low-level clouds cool the atmosphere. So the worst-case scenario is that high-level clouds increase and the low-level clouds decrease. But what actually happens is still a matter of uncertainty. There are lots of clouds are complicated objects when you start to look at them in detail. Anyway, so because of that, you tend to end up with, again, if you ask the question, how much will the planet warm if I say double the amount of carbon dioxide compared to pre-industrial times, so going from 285 parts per million, as it's called, of CO2 up to 560, how much will the planet warm because of that? And the models give a kind of a range of values, which vary from a little over 1 degree up to over 5 or 6 degrees. Now, anyone who has studied global warming would know that once you get over about 4 degrees, you're talking about kind of catastrophic levels of warming that it won't wipe out humanity. I suspect humanity is kind of as a robust enough species that it won't completely wipe them out. But with sea level rise and the kind of, types of heat waves that the human body can't withstand, we're certainly talking about, I don't know, I can't put a number to it, but a major loss of life, and on top of that, probably exacerbating it all would be that people who live in these areas where they're inundated or where life becomes unbearable because of the temperature, they will be moving polewards. And so the propensity for, unrest and war and all these sort of things is just becomes. So anyway, 4 degrees, for my liking, 4 degrees is kind of catastrophic levels of climate change. I don't think there's much doubt about that. So when you look at the models, you see it's probably around 40% chance, say. I don't know, it's hard to put a definite number on it, but it's around 40% chance of reaching those levels of warming. So then it's like the hiring the tent, or like the weather forecast, is that high enough to take precautionary action? Because precautionary action means cutting our emissions. And of course, the people who don't like cutting emissions, will say, well, it's expensive to do that, or it's going to disrupt the economy. Okay, fine. This is all to do with value judgment. So we have to decide. I know what I think. I think it's a no-brainer for me that we should be planning to cut our emissions. But I'm kind of, I accept other points of view. I don't think people are stupid. I mean, they're entitled to their points of view. But the most important point I'm trying to make here is that there are two sides here to this. There is the science, what the science says about the levels of climate change, and I'm trying to argue the point that in some ways it's no different to a weather forecast, in the sense that we can't say for certain that it's going to be a catastrophe, or it's going to be just something we can deal with easily. The uncertainties are such that one has to accept that one can't make absolutely definite deterministic predictions. And then the second point, which is kind of to some extent independent of that, is what do we do about that? What is that risk? Is that probability of catastrophe high enough that it warrants us around the world, trying to reduce that risk by cutting emissions? So these are two sides to the debate, and it bothers me. And I have to say, I think this is more a problem in the US than perhaps it is in Europe. But it bothers me that these two sides get extremely conflated and hard to kind of disentangle. But I think it's an important one to try to disentangle.
Well, Tim Palmer, before we get to our last topic, for people who want to learn more from you, maybe explore these ideas further, where should they look for you online?
I'm not a super social media person. I've done a few YouTube things. If you just type my name into YouTube, I think there's more than one Tim Palmer, so you may well get somebody else. But I've certainly got talks and interviews and various things on YouTube. I've written, the book, Primacy of Doubt. That's the US version. I have to say, this is the UK version, and I don't hope nobody from Basic Books is looking at this, but I actually prefer the front cover of the English version there. But anyway, inside the book, it's the same, so it doesn't really matter.
All right.
And my son convinced me to actually read the book as an audio book. So it was actually quite hard work, but I went into a studio in Oxford and physically read the book. So if you like people say they like my English accent from the US. So if you like my English accent, then you can hear me read the book in my English accent. If you can be bothered to do that.
Excellent. We'll put a link to that in the description for people to check out your book. And Tim, our last topic, we talk so much about all the uncertainty of life. What have you learned about dealing with the uncertainty of life?
I think one thing is kind of not to regret decisions that you make. I think it's there is a point here, by the way. People sometimes, there's a chapter in the book on COVID modeling. And, when COVID broke out, of course, the question is, what should we do about it? And actually, I got contacted by a number of people in the epidemiological field about trying to get my experience with ensemble forecasting of weather, because they clearly realized that this was the best way to make predictions of hospitalizations and deaths and so on from COVID. So not as one specific prediction, but as a probability. And indeed, the government, I mean, certainly in the UK, and I think the same is true in the US, the government realized that the decision about whether to have lockdowns and, stop people interacting socially was based not so much on the most likely outcome of deaths and hospitalizations from unmitigated social interaction, but from a plausible worst case scenario. So what they did was they asked the modelers, by a plausible worst case scenario, you could say, well, maybe kind of 1 or 2 standard deviations from the mean. Take the number of predicted deaths from COVID, to have an average, an ensemble average, and then you have some value which is, say 1 to 2 standard deviations. And what they decided to do was to take that was the number. That was like a bit like a probability threshold based on, the two standard deviations. So to take that as the prediction and say, okay, can we cope with that? And if we can't, then yes, we had better implement some social restrictions. So probability forecasting actually turned out to be quite important for COVID prediction. Now, some people then, this is the point I'm trying to get to here, some people argued after the event, they said, oh, well, but countries, I think like Sweden, which didn't have such severe lockdowns, didn't have as many predicted deaths as was predicted by this kind of two standard deviation value. And the implication was, oh, well, therefore the wrong decision was made. But that's incorrect. That's arguing, with the benefit of hindsight. There was no reason to doubt that these models were, biased in any way. And so a perfectly rational, I think, decision was made based on the probabilistic forecast for the model. The point I'm trying to make here is that what's the implication for life in general? I think when we do make decisions, we take the pros and cons into account. If they're important decisions, we think hard about them. And I think one important lesson from that is that if, what actually happens doesn't quite go the way you'd anticipated, don't treat that, therefore you made a bad decision. No, you didn't make a bad decision. You made the correct decision at the time, given the information that you had. And I think it's very easy in the human psyche to kind of regret things. Oh God, I wish I'd done that. Or I wish I'd bought, Apple stocks when they were, or whatever they were, when they were next to nothing. Well, yeah, fine, but you didn't. And that information that they were going to kind of go through the roof wasn't available to you. Don't regret things. Even though they turn out bad. And I try to kind of keep to that philosophy. That's certainly one philosophy that sort of taught me, my work has sort of taught me, don't regret. You don't have regrets.
Well, a great note to end on. Dr. Tim Palmer, thank you so much for this conversation, for your book, The Primacy of Doubt, and for taking this time with me. I really appreciate it.
Pleasure. Thank you very much, Brad.